this video, we will practice on the multiple choice question for the topic of counting and relation. I have taken the random question from this topic. Let's check it how to answer them. The first question we have taken as which of the following are the symmetric relation on this one? This is basically a set of integers. So on set of integer, we need to check which one is a symmetric relation. Symmetric relation means if ordered pair AB is a part of relation, then reverse order must be a part of relation. For the option 1, it says that the relation is the ordered pair such that either the elements in the ordered pair are equal or maybe with the negative sign. It means it is of the form this or A negative of A or negative A. Or we can also say that minus A because it is on the set of integer. The reverse order pair for this one is as it is, whereas its reverse order pair is this, and its reverse order pair is this, and its reverse order pair is same. It means for every type of ordered pair, we have its reverse order in a relation. So clearly this is a symmetric. The second option is we need to take the order pair where the elements are same. Means only this type of order pair we have. So clearly this is a symmetric relation. Why? Because its reverse order pair is as it is. So we can say that B is also correct option. Now what about the C option? We need to take the ordered pair such that A plus B is less than 3. So if it is a part of relation, what will be its reverse form? Means instead of this, if we write B plus A is less than equal to 3, whether this implies this? Clearly there is no change by writing in this form. So this implies the ordered pair is the part of a relation and hence relation is symmetric. At last we can say that D is the correct option. The next example we have which of the following is true for the divider relation on the set of positive integer. Only on the set of positive integer. Means the set starts from 1, then 2, 3 and continue this. Divider relation means A divides B. We need to take the ordered pairs A, B such that A divides B means 2 divides 16. So we will take the ordered pair 2, 16. But we will not take 16 2. Why? Because 16 does not divide 2. So such ordered pair is not there. It means it is not a symmetric. Whether this is a reflexive, whether every element divides itself, yes. So clearly divider relation on the set of positive integer is reflexive. So hence we can discard the option C as well. Next example we have which of the following relation are transitive on the set of integers. So we need to check for the transitive. Transitive means if the ordered pair AB is a part of relation and ordered pair BC is a part of relation, this implies AC ordered pair must be there. So for the first option, we need to take the ordered pair such that A is greater than equal to B. Means if it is a part of relation, A is greater than equal to B. And if it is a part of relation, B is greater than equal to C. Whether this combine implies A is greater than equal to C? Yes. So it means this is a transitive relation. What about the next case? If A is less than equal to B and B is less than equal to C, whether this implies A is less than equal to C? Yes. The third case, if A is equal to B and B is equal to C, whether this implies A is equal to C? Yes. So it means all three options are correct. And finally, we will mark the option D. The next question we have, which of the following is true? Greater than equal to is a partially ordered on the set of integers. Partially ordered means if it is a reflexive, antisymmetric, and transitive, then we will call the relation as a partially ordered. Whether this relation is partially ordering on the set of integers. For reflexive, we just need to check whether every element can be written as greater than equal to itself. Yes. For transitivity, if A is greater than equal to B and if B is greater than equal to C, can we say that A is greater than equal to C? Yes. What about the antisymmetric? How to check that one? In antisymmetric, we can avoid the equality and we can directly deal with the inequality. If A is greater than B, whether this implies B is not greater than A. If yes, then it is an antisymmetric. Because as per the antisymmetric, we have the condition if A-B order pair is a part of relation where A is not is equal to B, this implies reverse order should not be there. So if it is a part of relation means we are getting this form and we deal with non-equal elements means equality is removed. Now can you say that reverse is not there? That B is not greater than A? Yes. We can say that greater than equal to is the partially ordering on the set of integer. What about the divisibility? Divisibility is the partially ordering in the set of integer? No. Why not? Because it is not reflexive as well as antisymmetric. Why it is not a reflexive? Every element divides itself. Yes, but except 0. In set of integer, we have 0 as well and 0 does not divide itself and due to which it is not reflexive and hence divide relation is not partial ordering in set of integer. So in the previous example, we have taken the set of positive integer, not the integer. So this option is completely incorrect. What about the next case? This means as a subset. Subset is a partially ordering on the integer. Subset is defined on the collection of sets, not on the set of integer. So this option is again incorrect. So it means only option A is correct. Another example, suppose R is a relation on the set of strings of English letters such that A is related with B if and only if length of A is equal to the length of B, where Lx is the length of the string X. Then we need to check whether R is reflexive, symmetric, transitive or all of these. For reflexive, what we need to check whether A is related with A. So if A is related with A, according to the condition, length of the string A is equal to the length of the string A. And that is always true. It means relation is reflexive. Now for the symmetric means if A is related with B, then B must be related with A. So if A is related with B, this implies length of A is equal to the length of the string B. Now can we say that length of B string is equal to the length of A string? Yes. So it means R is clearly symmetric. For the transitive, we need to check if A is related with B, B is related with C, whether A is related with C. Let's check it. So if it is there, it means length of A is equal to the length of B string. For the next case, length of the B string is equal to the length of C strings. So whether this implies length of A string is equal to the length of C string? Yes. So it means it is also a transitive. Hence, D option is correct. The next question is, which of the following is true? The relation greater than equal to is the partial ordering on the Z. Yes, we have recently covered this one. Divisibility is a partially ordering on the set of positive integer. Yes, not on the integer but set of positive integer. Divisibility is a partially ordering. And the C option is also correct. Why? Because here we have the power set S and this is a subset relation. So every set is a subset of itself. Yes. So it means it is a reflexive relation. Now, if A is a subset of B properly contained, can we say that B is contained in A? No. And that's what we needed in the antisymmetric. For transitivity, if A is a subset of B and B is a subset of C, can we say that A is a subset of C? Yes. So it means this is the transitive relation. So this means the relation is transitive and from here antisymmetric and from here reflexive and hence it is a poset. So final answer is D option. Next question we have, if the relation is antisymmetric, transitive, reflexive, then R is called what? This is the definition of partially ordered set and hence the option is correct. Next case we have, if we have the binary relation ordered pair AB such that elements are equal on the set of integer, then which one of the following option is true? Whether R is reflexive? Yes, because every element is related to itself in this case. But whether this is the only option? No, because we have the element of this form in a set that is also a symmetric. How symmetric? Because its reverse is itself. So it is also symmetric, not only reflexive. So even A and B option is discarded because here it is mentioned as only. Now whether this is an antisymmetric? Yes, because in antisymmetric such ordered pair are allowed, but if A is not is equal to B and AB is a part of relation, then reverse should not be there. In this case, we are not taking such elements in the relation, so clearly this is an antisymmetric. But we will not say that only reflexive and antisymmetric, and due to this what this option is discarded. And also this is the transitive relation. So remember that this relation is called as the identity relation or equal relation. And this relation is always reflexive, symmetric, antisymmetric and transitive. Next example, if A contains these four elements and we have defined the relation as an ordered pair AB such that mod of A minus B is equal to 7, then how many elements are there in the relation? So we need to take the ordered pair such that the difference is 7. Now whether the difference of 1 and 2 is 7? No. What about 1 4? No. 1 6? No. 2 6? No. 2 4? No. 4 6? No. So there exists no pair such that their difference is equal to 7. It means the answer is D option. The next example we have, suppose A is a set that contains these three elements A, B, C, and here we have taken the equality relation. Means A is related with A, B is related with B, and C is related with C. And recently we have covered that identity relation is reflexive, symmetric, antisymmetric, and transitive. Which of the following option is correct for R? Whether R is equivalence relation? Yes. Because it is a reflexive, symmetric and transitive. Whether R is a partial ordered relation? Yes, because the relation is reflexive, antisymmetric, and transitive. It means option A is correct.